Okay, hi everyone. Oops, let me maximize the screen. So today we're gonna start module 3, which wraps up chapter 2. I was debating to either start start module 3 with semiconductor right away to get a little bit more exciting, or just wrap up the previous chapter on resonance circuit. But so I decided to just make it easier to follow because you guys are already thinking about high pass, low pass filters. So this will add just one more component to your circuit, which is an inductor. I'm going to write in red. Let's do that. Okay. So these are known as resonance circuits. Sometimes they're called band pass filters. We're going to see why that's the case. What else is it called? Sometimes, there's an inverted version of this called a notch filter, which you can make out of this. I think if you take the output from between the L and the C, you get that. I think there's another name for this. Yeah. So, so in this circuit, this is a L and a C, an inductor, a capacitor, and a resistor, all in a line. And we're taking the output between the capacitor and the resistor. Okay. So this is known as the series. I'm going to write it out in big words here. Series RLC circuit. Okay. Specifically the series part, because what you guys will actually do in the homework. So that's the other name. RLC circuit. What you guys will do in the homework, you could do the parallel version of it. So where you have the resistor first, and the L and the C are actually parallel to each other instead. They'll have similar behavior, but not the same. So anything we derive in this section will only be valid for the series version of the RLC circuit. And what you'll do in the homework, you'll have the parallel, too many R's, RLC circuit. That's what you guys will get to do. And I'll do the series version. Okay. Okay. So to analyze this circuit, we're going to use our impedance, or the book calls it, capacitive reactance. I'm just going to use the word impedance. Okay. So the impedance of a capacitor is I over omega C. The impedance of an inductor is negative I omega L, which is what we found in the previous section. Okay, what I'm going to do is I'm going to box this together and just combine these two components together. Okay, and since they are in series, and impedance is basically acts like resistors, right? You can just add them in without having to deal with the reciprocal and all that stuff. And the idea is that we're going to end up with something that has an impedance LC, and then we're going to have the impedance of a resistor, and we're taking the output here. You can see that this becomes basically a voltage divider, which is pretty easy for us to analyze. So the impedance of the LC part is the impedance of the inductor plus the capacitor together. You add these together, right? Just bringing them down. So what we're going to do first, before we move on, is simplify this a little bit. Maybe not simplify. We're going to massage this a little bit so that we can actually see something interesting right away. Okay. So the book skipped a bunch of algebra step. In fact, the book made an algebra mistake. There's actually a negative sign between the two. So I'm going to show that to you explicitly. So I omega L. I'm going to write these numbers out. And give myself a little bit of space to add some factors. So that's how you analyze this. Okay. So what I want to do is be able to pull out a negative I, a L, and an omega. So the first term doesn't have an L, or has the L, but does not have an omega on the numerator. So what I'm going to do is I'm going to multiply the bottom of this first term with omega, but since I multiplied the bottom of first with omega, I have to multiply the top with omega. Therefore, I'm actually just multiplying by the number 1. Okay. Similarly, right? The second term is missing an L, right? So I'm going to multiply the top bottom by L and then the top by L. Therefore, I can actually pull those out when I factor out. Okay. So the next thing, right? I want to pull out a negative I, right? I want to pull out the L, pull out the omega. What's remaining in here, right, is actually the omega square, because that doesn't get touched. And then on the second term, since I pull out negative I end up with a negative sign between them. Okay. And I pull out the, and what's remaining is actually CL in the denominator. And that's how you get to this point on your equation here. Okay. Then, right, what notice is that omega square minus omega square minus 1 over LC. I'm going to switch the order of this so it's the same as the book. Okay. That's sort of interesting because, right, if 1 over LC, well, actually, if omega squared is exactly equal to 1 over LC, right, this term completely goes to 0. Therefore, the impedance of your inductor and capacitor combined together, the impedance goes to 0. It becomes just a wire, which is sort of neat. Okay. So in that case, what happened is that V in becomes V out, right? Because we're taking the V out through the inductor and capacitor. Okay. This is known as the resonant frequency. Okay. What we're going to do is we're going to define the resonant frequency as 1 over square root of LC. That way, when you plug it into this equation, right? When you plug this equation, the square, it gets the square. Bleh. When you plug it into this equation, right? This when you square it, the square root goes away, and then you basically have 1 over LC minus 1 over LC, and the impedance of the LC part of your circuit goes to 0, and then your transfer function, which you will calculate next, goes to 1. Okay, so that's the reason for defining this new frequency 1 over omega C. Okay, this is known as the resonant frequency. Oops. Resonance frequency. In this case, the angular frequency. Okay. Okay. To complete the analysis to calculate the transfer function, we're just going to use the voltage divider. You can use Ohm's law and Kirchhoff's law if you want, but the voltage divider is based on that. So to calculate the transfer function at the output, basically you have something with impedance here, something with impedance here, and the voltage out is going to be equal to the bottom, which is ZR, which in this case is going to be R, right? Divided by the sum of these two things, R plus ZLC, right? And that's what this starts at. Okay, so R is just R. ZLC is going to be what we calculated, and we just plug that in there. Okay, we're going to massage this a little bit more. Okay, we do a little factoring and move things around so that we end up with a bunch of factors of I omega RL. You have this resonant frequency term here, and then plus another imaginary term I omega RL. So you can see that these two are very similar to each other. So in fact, we're going to get rid of the R over L because, right, because we're going to see this over and over again. And this R over L is actually, oops, another constant, kind of like the resonant frequency, where we're going to call that gamma R over L. And this is known as the RL constant, at least from what I remember. The book also calls it the dampening constant. Okay, just sort of neat. Because it does, the bigger you are, the more energy gets dissipated through your circuit, and therefore it's actually reducing the the output. Okay, so the two constants that we define in this derivation is this omega naught for LC circuit. Okay, that's the resonant frequency or the LC frequency. The other constant we define is also the gamma, which is R over L. I call it the R over L circuit constant, or the damping circuit constant. So with that, the transfer function gets a little bit cleaner, right? You still have a bunch of imaginary numbers here. So I omega gamma, you have the resonance term, and then you have another I omega gamma on the denominator. You want to so a lot of times we're going to try to figure out the amplitude, the magnitude of the transfer function, because we're interested in V out over V in. So if you take the complex conjugate and do all that multiplication, you end up with the transfer function being omega gamma square root, because that often happens, right? Because we're taking a complex conjugate and square rooting it. The resonance term, and then omega square gamma square. So we're going to just look at the asymptotic behavior of this transfer function, just as a reminder, right? When we did like RC circuit, like if omega goes to 0, the transfer function goes to, let's say it's a high pass filter, so that'll goes to 0, and then omega goes to infinity, then the transfer function goes to 1. And we'll see if this also happens with this particular circuit. Okay, so the transfer function as omega goes to 0, I'm going to do a little board erase kind of algebra here, right? If this goes to 0, this goes to 0, this goes to 0, so both these terms are gone. You have 0 over a non-zero number here, right? Okay, 0 over a non-zero number means the whole thing becomes 0, right? Okay, I'm going to do a little erase, and then now we're going to do omega goes to infinity. And you would expect, well, if we know that omega goes to 0, the transfer function goes to 0. Well, maybe the transfer function goes to 1 and infinity. So, but we'll see what happens. Okay. So if omega goes to infinity, right, you have one factor infinity on top, and then, but then you have omegas on the bottom also. So that's omega square here, but that whole thing gets squared, right? So this term actually has a power of omega to the 4th power, still unknown the square root. This term has power of omega to the 2nd power, so it doesn't actually matter as much. So the whole denominator, since you're square rooting it, is proportional to omega to the 2nd power. So you have the numerator proportional to the omega to the 1st power, the denominator being proportional to omega squared. The square is going to win out, so therefore it's still going to go to 0. Actually, this goes to 0. Not equal to. Okay, so on both ends, high frequency and low frequency, your transfer function goes to 0. I'm going to do one more calculation, is where omega approaches your resonant frequency. And I think you already kind of already know what that's going to do. Okay, so I'm going to do more board erase algebra here. So if this goes to omega naught, right, it's just some number, I'm just going to put knots everywhere. Okay, this term goes to 0, right, because omega naught squared minus omega naught squared is exactly 0. Okay, so this becomes omega gamma square root of omega naught gamma, both the squares. The square root actually knocks out the squares, right? So you have omega gamma divided by omega gamma, which is 1. Okay, so the transfer function at omega going to omega naught actually goes to 1, which is where your resonance is. Gonna look at this on the plot. So when omega goes to omega naught, which is exactly at this point up here, your transfer function goes to 1. Okay, as omega goes to 0, your transfer function goes to 0. As omega goes to infinity, your transfer function goes to 0 also, which is kind of neat, because now you're kind of like have a circuit that picks out one frequency. Well, it picks out one frequency the best, but then it does the other frequency kind of okay, and then it goes away, it goes away, it goes away, right? In fact, this is the RLC circuit that's used to basically send and receive the first radio transmissions in the 1800s. If you look on Wikipedia, you'll see this circuit here. And in fact, this circuit is about the size of a little table. It's not that small compared to what we do. You can actually see the RLC components. So this is actually the inductor because it's just a large coil. Over here is actually the capacitor. You can see that they're little parallel plates that you can adjust by dialing the knob. I can show you some of these in the lab if you want. The resistors are actually a little bit behind here. You would think these are a resistor, but this is just an isolator here that just keeps it from arcing. And they're still used today. So if you're these bandpass filters or resonant circuits, right, allows you to send and receive signal from between your cell phone and your cell phone tower. So your phone actually has one of these in there. Actually, it probably has 4 because I think they use multi-band cell transmissions. Okay, and then you can send and receive signal of a particular frequency between your phone and your cell tower. Your Wi-Fi router has one of these, etc. So all these wireless communication happens because you're actually able to pick out a particular frequency and therefore determine the amplitude of that particular frequency. And you can use, if you're using amplitude modulation, you'll be able to decipher the information being transferred back and forth. So that's the circuit itself. What I'm going to talk about next. This circuit allows us to bring up an interesting interesting concept that basically a lot of electrical engineer will use. In fact, it's also used in other part of physics, such as building resonators for lasers. So if you want to amplify a laser, you want a very good resonator. This is known as the Q factor. We're going to calculate this twice, and we're going to see how those two numbers compare, two quantities compare to each other. And we're going to see something special happen because it's physics. So what we're going to do is we're going to calculate the Q factor by similar definition of what we did with the RC circuit using this F3 dB point. Remember that for let's say a low pass filter, I'm going to draw the axes in black. Right, you have the transfer function, magnitude, you have some frequency in terms of like omega RC or something like that, right? And if you have a low pass filter, you start with 1, and then you go down and go down and go down, and then this will be 0.0707, which is equal to 1 over square root 2. Remember those numbers, okay? And this is a special point because that's actually where omega equals to 1 over RC, right? So you get exactly 1 here. This is known as the F3 dB point because if you convert this to the attenuation version of it, this is exactly equal to -3. Okay, so you have some transfer of plotting to go between those two concepts, but they're always called the F3 dB point. It's not called the 0.707 point, but they are actually the same thing. Okay. What we're going to do is we're going to do the same thing for our RLC circuit, where we're going to go down by to the F3 dB point. So on this plot, it's kind of hard to see. We're going to have a zoom in version of it. We're going to figure out how wide this width is, okay? And that'll allow us to quantify how the width of our filter, and therefore, how much other frequency sneaks in if we built our circuit like this. Okay, so the F3 dB point is defined by the transfer function being 1 over square root 2. Okay, so what we're going to do is we're going to equate the transfer function for our bandpass filter to be that, and that's the equation that we got from previously, right? We're going to equate that to 1 over square root 2. Okay, you square both sides because you have a bunch of square roots, and I don't want to deal with square roots. You clean up a little bit. Some of the factors of omega square, gamma square goes away, subtract each other out. You end up with this equation where it's omega square minus omega naught square, the whole thing square, equal to omega squared gamma squared. So this is a quadratic equation. It has two solutions. You can plug in your calculator to calculate this. And what you end up with is that omega, the solution to this, where you get 1 over square root 2, is that omega at the F3 dB point for our bandpass filter, okay, or RLC circuit in series, is going to be equal to gamma over 2, the whole thing square, plus the resonant frequency square, plus minus, because you have two solutions in a quadratic equation, gamma over 2. Okay, I'm going to describe this pictorially on the transfer function plot once again. So this is the zoom in version of it. So here, right, at 1, right, this is where you have the resonant frequency, right? Okay, transfer function equals to 1, right? Oops, not 0, 1, right? Then what we're interested in is the F3 dB point, which is slightly above 7.7, right? This is 0.707, which is 1 over square root 2, right? And of course, there's another one of this. So there's one on the left-hand side, there's the one on the right-hand side, okay? And so this is 0.707 also. So the plus solution here corresponds to omega 3 dB plus, right, gonna be square root of gamma over 2, the whole thing square, omega naught square, right, plus gamma over 2, okay? And we're gonna have another point here, omega 3 dB, the minus solution, right? That's the same thing, that whole square root thing. I'm not gonna write them again, oops, and of course the part I do write, it's supposed to be minus over 2. So that's sort of very interesting, right? Because, right, you can figure out where the omega 3 dB point is, right, by literally figuring out where your resonator goes down by a factor of 1 over square root of 2, either on the positive side or the negative side, okay? And you can physically just measure this in a lab if you want, okay? Okay, so going from the center to out here, right, the width of the to go out that far is gamma over 2. To go to the negative side, it's minus gamma over 2. And then if you add those two together, you have gamma. And this gamma is known as the full width half maximum. Okay, half maximum. Okay, so you may be debating, it's like, wait, why is it called half maximum? It's not the 0.707 maximum, right? So in signal transfer, what you're actually interested in is actually not the voltage or the amplitude transfer, because this transfer function is calculated for voltage output, right? So the power output of some circuit is proportional, it's not equal, to the voltage square, right? And then the voltage square in this case is proportional to the transfer function square, right? So, right, in this case, remember 707 is actually 1 over square root of 2. So if you square that, you actually get 1/2. So at these F3 dB point, you actually have half the power output, okay? And that's what you're interested in. Okay, so we're going to define this gamma, right, which is actually R over L. It's just some components we put into this in the circuit, right? That's actually the full width half maximum of your bandpass filter, so that you can quantify that, okay? Of course, this frequency, right, is not exactly useful yet, because if you, let's say you have, you're trying to transfer something at 1 megahertz, right? Let's just say that, right? And then your delta omega 3 dB, right, is 2 pi times some delta f, right, some frequency that you're interested in. And let's say this f is, you know, 1 kilohertz, just to make the math simple, okay? Times 1 kilohertz, so there's no delta anymore, right? 1 kilohertz might matter a lot if you are transferring signal that are 1 kilohertz also, but if you're dealing with transferring signal that are 1 megahertz, you don't actually care about that 1 kilohertz because it's 1 in 1,000, right? So the thing we want to actually quantify is some ratio of this delta frequency divided by, actually we want the numerator, the frequency that we actually want to transfer the signal from, so that's just the kind of like around the resonance frequency, divided by some delta frequency, which is the width, right? This is the width, this is the resonance. And you actually end up with something that's unitless also, and therefore applies to everything. Okay, so to account for the mean and the width of this, we can use this thing called the Q factor. So the Q stands for quality sometimes, but it's not exactly that, because sometimes it's not, you know, the more quality component you have, you may not have a higher quality resonator. It's just picking your components out properly. Okay, so the way we define that is basically the resonant frequency divided by this delta resonant for delta F3 dB that we just calculated, or the full width half maximum. Okay, and omega, right? Omega naught is the resonant frequency of the oscillator, the resonator, okay, which is 1 over L square root of LC. Gamma here, right, is the RL constant. That's why it's easy for me to remember, because I can just write it if I say RL constant. Okay, you calculate this, simplify a little bit. The Q factor is actually square root of L over R divided by R times square root of C. Okay, so you can actually calculate this Q factor, right, using your L, your R, and your C value of your circuit. Okay, and you can do the same thing, right? And this should be exactly the same as what you measure if you measure this F3 dB point and measure where your resonant frequency is at. Okay, so which is sort of interesting. Okay, because you can, so this is how you calculate it on paper. If you go in the lab and you try to measure it, you want to measure F3 dB, right? And then you want to measure the full width half maximum of the negative 3 dB point of the frequency, right? So it converted everything to just frequency, because that's what you'll see in the lab, not omega, right? It's the same thing, because you just divide by 2 pi the numerator and denominator. Okay, so this is what you'll do in the lab. Okay, yeah. So that's the way we calculated the Q factor for using this F3 dB definition, which you will be able to do in the lab. There's a more theoretical calculation, like we'll call it the fundamental definition. But another way to think about this is just in terms, the Q factors in terms of energy. The way you calculate this is that, well, Q can be defined as how much energy gets stored in your resonator, right, divided by how much energy is lost out of that circuit. And want to calculate this per cycle, because every time the input goes up and down, you want to figure out how much energy is lost per cycle. Okay, and we're going to put a 2 pi in front of it, because that's going to be nice, and we're going to see how that factor cancels out. Okay, so how much energy is stored in our resonator? Okay, so for the energy stored in the capacitors, it is actually proportional to how much charge is on each of the plates, right? And that's proportional to the voltage across that capacitor because of QVC, right? So therefore, if you average over time, the amount of energy stored in the capacitor is actually 1/2 times the capacitor's value times the voltage square. This 1/2 here comes from the fact that if you're sending in a sine cosine signal, the energy is proportional to the voltage square. When you square a cosine function, you're going to shift the whole function up by 1/2 the amplitude. Okay, If you want to know how this is exactly derived, I suggest you go look at your general physics textbook when they start talking about AC current and AC power. I think one of my lecture videos on YouTube also has that too. Okay, but we don't like this, averaging thing, right? So what we're going to do is we're going to define this RMS voltage, where RMS voltage is 1 square root of 1 over square root of 2 of the peak voltage. In fact, this is how we actually define the voltages at our outlets, because the outlets we have here, they're called 120 volts. Well, in the US it's 120 volts. This is actually RMS voltage, not the peak voltage. So the peak voltage in the US is actually about 170 volts. Okay, and so if you want to test something using it with the outlet, I don't suggest that you do directly, right? The highest amplitude voltage you actually have to worry about is 170 volts, not 120 volts. Okay. Anyway, so the energy stored in a capacitor is 1/2 C times the voltage, RMS voltage squared. Okay. Similarly, if you do this calculation for an inductor, where in an inductor, the energy is stored in the magnetic field. In the magnetic field density, the density of the magnetic field inside your inductor, and the magnetic field is created by the current. So therefore, in the inductor case, the energy stored is actually proportional to the current square. We play a similar trick here where we define the RMS current to be 1 over square root of 2 of the peak current, and therefore we end up with something that's very similar to capacitor. It's just 1/2 the inductance, how many current loops you have through that inductor, times the RMS current square. So what's sort of neat about this is that when your circuit is on, let's put the inductor over here, the energy in the inductor and the energy in the capacitor are just kind of sloshing back and forth between them. When the voltage is very high, what happens is that a lot of the energy gets stored in the capacitor. When the current is very high, a lot of the energy gets stored in the inductor. So as the voltage gets to its peak, all the energy is in the capacitor. When the voltage goes to 0, at that point is the steepest part of the cosine function, right? So therefore, the current is actually maximized there, and at that point, the energy is actually stored in your inductor. In fact, if you compare these two quantities, they're actually exactly the same. So we're just going to use the inductor part, okay, instead. Okay. All right. So with that, let's see. Oh, with that, so that's the energy store. That's our numerator. That's checked, right? All right. The energy loss per cycle, okay, and the energy is lost through the resistor, right? Because it's dissipated through the resistor. The power lost through a resistor is just the current times the voltage. It's the same thing as I times V, right? But it's the average version of it, so therefore you have this RMS stuff, okay? All right, so we're going to plug both of these back into the Q factor equation that we made up, and hopefully everything will work out. Okay, remember that equation is 2 pi, and we're going to see how that 2 pi plays a role. The maximum energy stored. So how do we do that? I'm going to write this on the right because I think the book skips a lot of steps. We have a 2 pi, the energy stored, right? The energy stored is this 1/2 L I RMS squared, right? Let's just use that version. I RMS squared. Sure, that's an L. Okay. The energy loss per cycle. The energy loss per cycle. So we have power loss per second, right? That's right. So we have to multiply that by something with units of time. So per cycle meaning 1 period of the input, the Vn function, right? So therefore, right, in this case, it's actually the P, oops, not P, I RMS times the voltage RMS, right, times the period. So this thing called T here is the period, right, and it's defined as 1 over the frequency. So 1 over the frequency is omega over 2 pi, which is actually 2 pi omega. And we're going to see how that's, you see where that 2 pi is going to be useful soon, right? Okay, so L. Okay, so in this case, right, so one factor of the RMS cancel out. But then you have this ratio of I RMS over V RMS, right? Since these are concerning the resistors, right, there's only one current, right? So this 1 voltage is actually across the resistors. That's how we calculate power. Okay. That case, right, we can use Ohm's law. So V RMS. So V, I'm gonna play a little trick on you guys. V equals IR. We're already happy with that. What I'm gonna do is add RMS on both sides. And why is that equation valid? Right, I'll derive it. It's just a one step, right? If I do this, right, 1 over square root 2 I. So I'm multiplying the same thing to both sides. So this becomes V RMS I RMS times R. So I RMS divided by V RMS, right? I'm just going to solve this for R, right, equals to R, right? So this whole thing actually ends up with a resistor on the bottom here. All right, we still have the 2 pi times 1/2. You still have an L there. Now you have an R on the bottom, and the period, right, is 2 pi over omega. And since we're concerned with how much, what's the Q factor near the resonant frequency, this is actually going to be the resonant frequency. Okay. All right. Get everything right? Yeah. So the 2 pi actually goes away. Let's see if the 2 goes away. Ooh, okay, so let's continue on. So this is L over R, and then you have denominator, so which goes in the numerator actually. So my fraction is actually a little bit slanted, so let's do that. Okay, so this is pretty close to what the book has, so I didn't make one mistake, right? So up here, right, where we said that, well, the energy in the capacitor is the same as the energy in the inductor, I put only one factor of this. Okay, so actually in this case, right, the energy of the capacitor plus the energy of the inductor, of course, is going to be twice that. So, so it's actually 2 times L by RMS square. So these actually cancels out this 1/2. So I'm going to do a little board erasing once again. So this goes away, and this 2 goes away. Now we have exactly what the textbook does. Okay, and R over L, of course, is gamma, and therefore, right, the Q factor is actually just omega naught divided by gamma. And how does that compare? Actually, in fact, right, it's better to compare it without plugging in this omega naught, gamma naught thing, right? So omega naught is actually 1 over square root of LC. Gamma is R over L. Okay, so half a factor of this cancels out with this, right? So we end up with square root of that. So this is actually, so the Q we get is actually, so this is in the denominator. Oh, this is in the numerator, so you have a square root of L on the numerator, and then an R on the denominator, and a square root of C on the denominator. This is the energy version. I'm going to go upstairs and copy down the F3 dB version. Okay. Right. The F3 dB version is exactly the same. Okay. Okay. And this you can measure, right, in the lab with the resonant frequency divided by the width, full width half maximum of that, for the F3 dB point. these two are the same. It's cool. So this is where it's really nice, where you can do a completely theoretical calculation where you're just thinking about, oh, how much energy is stored, how much energy is lost, right? Come up with the Q factor. Or you can do the same calculation. Okay, where is this resonator loses half its energy, right? Or the power, right? Because the F3 dB point actually tells you where it loses half its power. Okay, that's why it's called a full width half maximum. Okay, and you come up with exactly the same thing, which is extremely neat.